Um, so I'm taking the English dataset. I'm sampling a bunch of points, 20 rows from it, and I'm selecting the variables in which we are interested to, which are the lexical decision time, the logarithm of the lexical decision time, and the familiarity. And I'm going to see what are the residuals. So let's take whatever line. So let's take first. Let's plot this variable that we just defined. So you see that we did not make any error. So you see there are so only 6 rows. Why? Ooh, doesn't make too much sense, but let's see. This function sample n. Sample n rows from a table. So um, so it should be correct. I don't know why. Hmm? Do you have any idea why it is simply it has 6 rows? I don't. Of course, I plotted only the first 6 rows, so header plots. Okay. So it should be, if I remove head, it should be 20 rows. Yes, 1/2. So this command did what we wanted to do, and let's plot, ggplot it. So the data is now in. Then on the x-axis we put the familiarity. On the y-axis we put the lexical decision time. Then we plot the points. Now the plot is clearer, and let's take whatever line. So whatever beta 0, let's take beta 0 equal, I don't know, but whatever line that it passes next to this point. So let's say that at 0 it will be around say 8, and so beta 0 it's not 7.5, and beta 1 it's equal to minus, say, let's say minus 0.2 is the slope. So these are completely numbers that I'm guessing, and now I compute what are the residuals. I plot what are the residuals. So first, let me plot the line. The slope, sorry, the slope is beta 1, and the intercept is beta 0. Now we should see a line here. Slope is beta 1. So this line passes at 2, it will pass at, okay, I exaggerated the intercept. Ah, okay. Of course, thank you. Okay, now we see a line. And let's paint it with red. So what are the residuals? Well, the residuals is this is the line of your predictions. The residuals are the vertical lines that are the like here where your prediction are these ones. So and the residuals are the difference between your data and the things that you would have predicted. So your data is the following: x1, y1, xn, yn. And remember that you want to use this information to compute beta 0 and beta 1. Now you try to guess beta 0 and beta 1. What the errors are y1, for instance, minus the predicted value, which is minus beta 0 plus beta 1 y1 x1. So does it make sense? This is the first residual. Sorry, yes. And you can do it for every residual. Does it make, do you have questions? Okay. For completeness. And I think the last residual. Which again is the predicted yn is beta 0 plus beta 1 x. So let me, in this picture, let me plot this residual. So now it will be a little bit a code which will be a little bit of a mess. So we save this plot into a variable h. Now we do a for cycle. Since I want to put 20 segments, there are 20 points. The for cycle will have 20 will be we will enter into this cycle 20 times, and we save a segment in each step. So in each step, h goes to h plus a segment. The segment will go from x, which is it's English is the familiarity. I. Then, so this is the first x. Then there is the y, which is the one that we have. So it is the English, the lexical decision time. So here we are taking the point, and then there is the other extreme, which has the same x, uh, and the y this time, sorry, the y in this is on the line, so it will be beta 0 plus beta 1 times the English familiarity computed at time. So now this will be, it's correct, but there is something which is called the lazy evaluation of the counter variable, so that error doesn't really count, doesn't substitute I into the function. It does it at the end of the cycle. So it will, if we do like this, it will plot only the last segment. So let's see. Uh, okay, we are not plotting anything actually, but at least it doesn't give us errors. So it plots only the last segment. So to deal with it, we have to use a package which is called Erlang. That avoids lazy evaluation. Lazy evaluation means exactly that it's lazy, so it postpones it to the end. So, but I mean, this is not nothing you have to learn, because when you find these issues, you Google for them and you will find the solution by probably. Um, and we can evaluate these expressions by putting this by using this notation. So putting a double point. Okay, Langer. No, I don't remember it. I have it here. So, uh, sorry. Um, um, so I did it here. So the package is mm, okay, here for the first time. Erlang, okay, without the capital letter. So now this is the plot. It should be correct. Okay, the basis y is not y is going to plus infinity. Y end. Um, okay, okay, okay. Now, these vertical lines are the residuals with, of course, they have a sign. So you have to choose the one which point, which are above the line, will have a sign. The one which will be below the line, they will have the minus sign. So, and if we, sorry, bad for the, how bad is the model? For the ordinary least square, means is computed by the sum of the sum of the squares of the residuals. So by, let's say, a function. This is a function of beta 0 and beta 1. Which is the sum of the residuals, so of the squares of the residuals. So this one squared plus. So, so I give you a beta 0 and beta 1. These quantities can be computed, and I look for the beta 0 and beta 1, which minimizes the badness. So R finds the minima, finds the minimum of the beta 0 and beta 1 that minimize the above one. So, as simple as that. Not very complicated. I mean, it's not even easy, but it's not the worst thing you saw in this course. What is more interesting is the statistic of that the function lm gives you back as output. So let's try to look at a couple of them. We save the output into this variable model. So let's go back and see it. If we simply plot it in this way, it will give me the coefficients. So I have to put a summary to see more in detail. Okay, well, this is some information about the residuals. The coefficients now. Okay, it gives us the estimate for the intercept and the slope. So what is it gives us some t-statistic and the p-value associated to this t-statistic, which is here very small. So what does this p-value refers to? Um, so um, so as usual, our hypothesis 0 is that our null hypothesis is that the model uh, we okay, maybe it's is that y is that the beta 1, let's say, let's look at the p-value for the familiarity. So this second row, our hypothesis 0 is that beta 1 is equal to 0. So this is the beta 1, which is ideal. So our beta 1 will never be exactly equal to 0, the one we find. And the alternative hypothesis is that well, beta 1 is not equal. And of course, all the hypotheses are true. So all that y is equal to beta 0 plus a noise. This is always in this framework. So with plus beta 1 we are always assuming this hypothesis. Otherwise, all the statistic will be random numbers. I mean, sorry, will be not. They won't tell you anything, and you will be misled by them. So, okay, so this is the test we are doing, and the p-value is associated to this test. Now, this is so this is a t-test actually. It's not different, and so the test R is performing is exactly the correlation test. Let's go here and try to do it. So let's try to do a core test between the variables in this English so English was if I remember well, was a table with two numerical rows. I don't know why he is telling me that. Okay. It's not really it's not so intelligent. So maybe it's better to do. No, let's do a correlation test where the x is equal to the let's try to see whether these two variables are correlated. So the reaction time and the familiarity. Okay, the p-value is small. Okay, it's not that small since this is the data set which have only 20 rows. So of course the p-value won't be that significant, as much significant as the other one. So let me also do a linear, do the same regression on these 20 variables and see that the p-values will be the same. So here you see there is the variables, the test done this time with of the beta 1 coefficient gives us a t-value which is minus 2.2 and a p-value which is 0.39, which is exactly is not the, yes, it is the exactly the p-value here and the same t-statistic. So it is not, you are not learning new math. You're just seeing it in another command. So actually, we didn't define how this core test work. So just to know, for you to know, this beta one is the test for this beta one is exactly the same. So do you have, do you have ideas of why the test for beta zero is really not important? I mean, we are testing whether the intercept, what is the intercept is where the regression line passes when x is equal to 0. Because if we substitute in the beta 0 plus beta 1 x equal to 0, we will get the intercept. Now, why it is not important to see if it is different from 0? I mean,
we, we, so beta one actually influences the trend, the tilt of the line, while beta zero just up and down.
yeah.
So, yeah. Beta zero is just for, it doesn't give us anything visual.
Yes, exactly. We are interested in the trend, in how x correlates with y. Moreover, 0 is a particular point. Maybe it's also outside the range of the x. If we think about x being the familiarity, there won't be any, we cannot extrapolate to x equal to 0 because the familiarity, let's look at the range. Uh, which values can take the familiarity? From 1 to 7. So why the intercept is not so important? Well, it doesn't give you a trend, as you said, and moreover, here x equal to 0 is not in the data, so in the range of the data. And what's important to understand is that we cannot extrapolate the information outside the range of x. So we have to have some mass of points around the point we want to predict. So let's go back here. So if I try to predict something here, it makes sense. I use some data that are here, but if I go to 0, there won't be points, and it doesn't make sense simply. So from here, the prediction would be good from 1 to 7, even from 1.5 to 6.5, something like that. But okay, beware of that. Don't extrapolate information. What else? What else? Yes. So the residual standard error. This is more interesting. No, the residual standard error is. Let's compute it. But the multiple R squared is nice. And the F statistic, it will be more interesting when we'll do multivariate regression. So the residual standard error let's see what it is. So I would say that is the standard error of the residuals. So let's try to take yes, it should be like the square root of the sum of the residuals, so something like that. So the residuals are saved in the variable residuals. Then we sum the square of the residuals, and we divide it by n minus 1 by the number of to the length of how many residuals there are there. So, and we subtract 1 because of the degrees of freedom. So maybe I mean it should be 0.14. Let's see if I'm right or not in this model. Yes. So it's simply the square root of this quantity here. We take the residuals, we square it, we sum it, and we divide it by the length of it minus these two, which is not really important. And then we do the square root.
So we need the sum divided by length, then the result is here.
Sorry, I use formula, it's better. So um, here the 2 is related to the fact that we are estimating two variables. So we fix beta 0 and beta 1. So we have two degrees of freedom that we are removing. I'm not an expert on it. So, but these two is related to the fact that we are estimating two variables, beta 0 and beta 1.
So the sum variable is
Yes, but I'm really yes, but it should be like that. But I'm not a statistician, so this is new. This to me also. So, uh, but I would say yes. Yes. Mm. I would say yes because probably when we will do I don't know, it won't change these two if we add more. Okay. When we do multivariate linear regression, we will change these two accordingly. So according to how many parameters we have to estimate. So this is the residual standard error. Nothing. I mean, when you see a standard error, it's usually an expression with a square root, and the residuals are an error. So okay, So more important than this is the multiple R squared. Mm, okay, let's take uh, so let's take a model, do the same procedure with a model which doesn't have beta 1. So if we take beta 1 equal to 0 and try to minimize so that y is equal to beta 0 plus an error, uh, um, and we do the same procedure, so and we try to minimize um, the sum of the residuals. So what do we obtain? Well, we obtain that beta 0 is the mean. These are computations that can be made. So, I mean, and you can see it from here, since the noise is mean 0. So the mean of y is beta 0. So the best prediction for the mean is the empirical mean. So this is equal to y1 divided by n. Now, it's whatever, you don't, I mean, apart from this fact, you will obtain a minimal residual, which is called, I don't know, let's do it, the computation. So let's take a linear model which we try to predict the reaction time of the lexical decision using a constant. And let's say let's save this into model 2. Will be for sure a worse model. So let's plot. Let's ggplot it. So uh, on the x-axis we have always the familiarity, and on the y-axis the lexical decision. Then we plot the points and the regression line of the simple model. So um, for the formula is we try to predict y using a constant. So now it should be a vertical, an horizontal line, the best line, centered in the mean. And let's plot by contrast also the regression line. Sorry. So you see this line is better, has a lower sum of squares of the residuals because of definition of the best line. So do you see that if we do if we sum the square of the residuals, the model one, or we sum the sum of and with the square of the residuals of the model 2, which will be bigger. The model 2 is this one, in which I try to predict y using a constant. Yes, exactly, because we are estimating the best. This function is what we are minimizing, and in the first case we use two variables, so we could be more precise. And let's check it. So the first residuals are 90, and the second ones are 112. So this R squared is simply so this will be always true. So this R squared is computed, tells you how much the model with beta 1 is better with respect to the model with beta 0, with only beta 0. So how do you do? Well, we divide the sum of the residuals. So this number here, which is smaller, we divide it by this number and we subtract so maybe it's better to have to find a good notation for this, but let's call R the residuals of for the model 2 with only beta 0. So we do this division. So this number at the numerator is smaller because we have seen it was 90, and on the numerator, sorry, the numerator is smaller, and on the denominator it's bigger. So this is a number which is smaller than 1 and greater than 0. So oof. And when is it? It is more. I mean, when will be on the next one? I mean, when will it be more close to 1?
So we propose it to one when the model is equal to one, is more similar to the more without.
Exactly. So if the residuals are more or less similar, it doesn't help you that beta one. So let's simply compute this division and then subtract it. So we have to divide this is the division above, and so we want a number which is close to 1 when the model is good. So we subtract this quantity to this quantity, 1 to this quantity, and we should obtain the R squared. So this is the R squared. Maybe let's go up here. And yes, it is R squared. So this is the meaning. Now, this what you don't need to know this, but of course, it is. Let me simply bound it with what we have seen. So actually, if we take the model 2, the second model, and we take the coefficients. So the intercept will be equal to the mean. This we already know this. The mean of the reaction time, because we are trying to estimate it with a constant. Now, the sum of the squares of the residual will be the variance. This is already, so the variance of the English will be the exactly equal to the sum of the squares of the residuals of the model with only a constant. So we have to divide it by 19, I guess, because we have only we are predicting it using a constant, so not the variance. What's happening here? So in summing the residuals, dividing them by 19, which should be okay. English has much more rows, so -1. So this is another way to see the variance, which I didn't actually ever explain to you. So if you go here, well, on the horizontal line, well, if we take the residuals and we square them and we sum them, we'll obtain the variance. So we can think at the linear regression line that it is explaining a little bit more of variance than the we are making a better guess, and this sum of the squares of the residuals will be less than the variance because and it will explain a little bit better the variance of the data. And to end this fancy part, the correlation, there why it is called R squared. Well, we can take the correlation, the correlation coefficient of this data set. Of the first column with the second one. So it was familiarity. We can square it, and we will obtain the R squared. So yes, it was. So this is why it's called R squared. It is the Pearson's correlation coefficient to the power of 2. I mean, to see this is not difficult, but you need to do derivatives to compute, to do computations. It's useless. But at least you know why it's called the R squared. So this ends the topic of bivariate linear regression. And we will start with, I mean, I won't spend too much time for the multivariate linear regression because it's exactly the same stuff. But maybe next hour we will do, yes, we will do some questions about what does this linear regression line tell you about causality. So if you look at this picture, you see this line. I mean, the thing that comes to your mind is that familiarity influences the lexical decision, which is true, but it depends on how, I mean, influence is a big word. So it can, to make it precise, it's, I mean, it's not that, so we're going to distinguish effects, uh, causal effects to simply that, well, if you see, if you're more familiar with a word, expect that the reaction time will be less, less big. But this doesn't mean that familiarity is the cause of the lower lexical decision. At least it doesn't tell you directly from this picture, because if we simply turn the computer and we look at the picture from the other side, we will see another regression line which will be different from the one. But on the x-axis, you will have the lexical decision. Y-axis, you will have the familiarity. You will have a regression line which is not zero. So if you conclude, or if you had concluded before in this picture that since the regression line is different from zero, familiarity influences, I mean, it's a cause of lexical decision, you should conclude also that lexical decision is a cause of familiarity, because if you base it only on this point, so causality is a much more, I mean, you have to have more information, and it's what we will see. So maybe let's do 10 minutes break. So we'll start another topic. Okay. So, so let's do the multiple linear regression. which the theory is exactly the same. Now we want to predict y using two variables. Let's call them x and oof. So z is not a good name. W is a good name. I guess. So let's take a data set. I don't know which can, but let's keep the English dataset, which have many rows. Many columns, sorry. And let's find another variable to try to predict this lexical decision. Of course, no, I need to check another stuff before going. I need to, sorry, not to check, to do another stuff, bivariate regression, which is important, which is to check the hypothesis. We made some hypotheses for the bivariate regression. So we made specifically the hypothesis that y is of this form. That's a noise. So we need to check that this noise is where epsilon is. Actually, at the beginning of the lecture, I said that is a noise, a mean zero noise. But actually, it has to be also Gaussian. So I have to correct it. So this is important. Otherwise, the statistics are computed using this hypothesis. And if we want to predict y and to make so to make this kind of predictions. Okay, here, okay, no, probably here is not. There are too many points, but let's go here. And let's do on this small amount of points linear regression. So so you see there is a confidence interval. You can use it to make predictions, and there are some computations which tell you the usual stuff, so that okay, your points with 95% of probability will fall into this area. So these statistics are computed using the hypothesis are exact if epsilon is a Gaussian noise. So we need to check this hypothesis, and the best way to do it, I mean, there is actually we called it model 2, no, sorry. Let's save the reaction time of the lexical decision predicted using the familiarity of the smaller dataset to model one, into the variable model. And there is this function, autoplot, which can plot this model. And it will give you, okay, no, I have to use also GG45. So library, I guess. And this function autoplot gives me some statistic that we can with which we can check if the hypotheses are satisfied. And the most important is this quantile to quantile normal quantiles and theoretical quantiles put together, and these residuals. So now there are, this is, I mean, I think it goes beyond the scope of the course to say, I mean, it would be nice, but we have not so much time to go into details in each one of these plots. But in this case, this there is actually a variable into this data set. So let me use the old data set, because 20 rows is too small to, let's check the whole data set. Okay. Let's look only at the first two. So the residuals like distribute around 0 quite regularly. So it seems that hypotheses are satisfied. So you don't see the blue line. I don't know really what it means. And the quantiles are practically, so do you want to do you want me to explain to you what is this quantile to quantile plot? It's a way to see the difference between the distribution of the residuals and the normal distribution. So on the y-axis, you have the quantiles of the normal. On the x-axis, you have the quantiles of the of our residual. So let me write it simply because so on the cuckoo plot, we can check how much normal is the distribution of our residual. The more the residuals are into this line, the quantiles are here, the more normal is the distribution. So how to explain it? I mean, we have a quantile is like let's take the residual. Let's let's first fix a number, alpha, which is a number between 0 and 1. And consider, sorry, the alpha quantile, alpha, I don't know exactly the name, alpha percentile probably, of the residuals is the point is a number. Let's call it R alpha. For which the residuals are alpha of the residuals. Sorry, not for which has on its left, has on its left alpha percent, alpha residuals, a proportion of alpha residuals on the left. Sorry, for which the number uh, for which like the number of residuals on its left is alpha percent of the total. Like one half is the median, because the median is a point where you have half of the data on the left and half of the data on the right. An alpha percentile is the same of the median, but done with an arbitrary number alpha. Uh, uh, so we can do the same for the normal distribution. So the normal distribution, the quantile for the normal distribution is y alpha, let's call it, such that the mass, which is the following, so this is the mass of the probability of falling on the left of alpha for a normal. Sorry, this is y of alpha. We have to normalize it. Such that, so this is what I'm writing here is the mass, the probability that a normal is smaller than a number y of alpha. And this number y of alpha is such that this is equal to alpha. So the above formula, so y alpha is said to be said to be the alpha percentile. of the normal distribution. And I don't know if you have ever opened an old textbook of statistics in which where people went really mad because at the end of this book there were a lot of tables, and those tables were basically computing these percentiles of a normal. And it was, I mean, a big part of the book because at the time, now it makes no sense to include them in a book, but at that time there were not, I mean, really smart people spent a lot of time doing something that now with a click we can do it in no more than a second. Uh, I have to sorry, I have to put the charge with the computer. So for each alpha, uh, we have the percentiles of a normal and of our residuals. Um, so we are plotting the cuckoo plot plots the points which we call the R alpha, Y alpha. So the percentile of the residuals and versus the percentile of the normal. And of course, if the residuals are almost normal, the percentiles will be similar. So the more, so we expect to see a straight line. If and this is indeed the case, more or less. But this is I mean, it's a step that you have to do. It's a crucial step because you are you are making an assumption. You don't know if this assumption is true. Maybe not, but at least doesn't have to give you a contradiction. So maybe, of, for sure, the assumption is false. So let's say this way, the model will not be, I would bet my hand that the model is not true, but maybe in at least if you believe that is true, the data that it gives you should be should not give you a contradiction. So if we see all the residuals which are completely completely non-normal, you will say, okay, no, it makes no sense to use a linear regression here. But here, the residuals they look very even too good for me, and the cuckoo plot is fine. The other two, I don't know. And so it's a step that you have to do. So to check a posteriori if the hypothesis is like, I mean, it's for self consistency. Now let's come back to the multiple linear regression. We have to choose another variable, and let's choose, I don't know, the familiarity, the length in letters. So where is it? So of course, the longer the word, the reaction time will be longer. So let's try to do it. To take this linear model, we try to predict again the lexical decision time using the familiarity and the length in letters. And let's see the data. Again, this. So now the output of this model is simply that the lexical decision is equal to 6.8 plus, in the sense of minus, 0.1 times familiarity plus 0. Okay, I have to go to levels of significance which are higher. So, something like this. Times the length in letters. So this is the how these coefficients are computed is exactly the same way. Now let's plot them just simply because we can do it with the library plot the uh, so we want to plot first the data. So x is say the length in letters. Y is the familiarity, and that is the what we are predicting. So it is the reaction time of lexical decision, and the plot is scattered 3D. And this I really not so sure what it means, but it has to be added. These plots makes a scatter plot in 3 dimensions, and you can interact with it, which is nice. So this is the so you have a discrete length in letter is a discrete variable. So you see that on the x-axis you are discretized. This is you can find, I guess this will be two. I mean you will find few words with 2 letters, 3, 4, 5, 6. Okay. So this is on the here you have the familiarity. By the way, let's see if the familiarity depends on the length in letter. So just for curiosity. So x is the length in letter, the field, and so I cannot see how many points. Of course, I cannot see the density of points, but okay. well, it doesn't matter. And then let's add the regression plane in this case. Um, yes, I have to do a little bit. So I have to take a grid of points. So this can be done with the command expand grid. So what does it do? I give some x values, some y values, and it computes like the grid with it computes a data frame with I mean it's easier to see it than to explain it. I mean you have some x values, some y values. It computes all the possibility, all the points that you can make by joining with the y values and the x values. So it is a grid in the plane. So we have to take what we have to take the length in letters. Well, the length in letters goes from 1 to 6. Let's say from 2 to 7, say. And while y, the familiarity, let's take, I don't know, the values that the familiarity has. And this gives me a grid. So uh, let's see this grid, what is. Um, so you see, there is the first column is made using the length in letters from 2 to 7, while the second one is made using the familiarity. And there are all the possible combinations. So for each value of familiarity, 3.17, you have 6 possible length letters. So this is only coding, so it's not very interesting. Let's add the Z. Now we use the linear model to predict, to compute, I mean, the Z, the lexical decision from the points of the grid. So and then uh, let's see if, familiarity. Uh, Okay. I have to call the X was the familiar. Sorry. Y X was familiarity, while the Y was the length in letters. Then I can predict Z, and I can plot also the plane, plane now. So I have to add the trace. Uh, as a 3D mesh where X is equal to grid, the first component of the grid, so familiarity. The Y is the second component of the grid, which is length in letters, and the Z is the Z. Now this should give me also the plane. I remember. Okay. It didn't build. So he computed the points. What happened? Okay, he computed the points of the plane, but they didn't really made a plane. So let me check the things that I did before. Um, so since I've made it before the lecture, let me check. Okay, what happened here? Reads mesh 3D at trace. Okay, it seems to me. Type, not mod. Sorry. This is a way to make a 3D plot, which is nice actually. I mean, nothing deep, but it's nice to plot these points and make the points rotate. That's, but you see now we are predicting this Z, which is vertical, using two variables, and the model is linear because you see it always has the same slope. It doesn't vary the slope, so it's a plane. And is the plane that minimizes the residuals. So we see that here it has okay, some slope, and here it has another one, which is, and the slopes are the one computed here. You see the slope of the x-axis, the length in letter is really small. So probably okay, this is the x-axis. Why? So what, I mean, why the slope is bigger in in the component of familiarity with respect to the, okay, this I'm plotting the z value x against z. So, and y is kept fixed. The slope looks more or less like a minus is okay, but it goes from um, from 6 x goes from 1 to 7 and z goes from 6 to 6.3. So like sorry, from 6.7 to, so 0.4 divided by 7, which is not that vabbè, okay. I would have thought that the, vabbè, it's not, it's not a matter of, so this, with this you can do the plots. Now, the statistic of this model, let's look at it because they are quite different. So, let's take a summary of this model. We have the coefficients and the usual test for the coefficients. So if they are significantly different from 0. And we see that the length in letters is not really significant, actually. Familiarity is much better predictor. Now, what's the, we go and see what is the adjusted R squared, which now is different from the multiple R squared. So when we add predictors, the multiple R squared for sure will increase because we predict we have a better model. I mean, which can explain the variance, but maybe it's due to chance so only, and really adding a predictor doesn't really get your model, make your model better. So the adjusted R squared is an adjustment made in order to penalize putting more and more variables. For instance, in this model, if we make the same stuff, so let me copy and paste it. But we add like a column of random numbers. So we add a column to this English data frame of random numbers. So they don't help you to predict because they are random. The length is usually the number of, so the column has to have the same rows as the English. So whatever. So, and let's call this column random. So now I try to predict Uh, this second this lexical decision using also random, which will not help me for sure. Names are duplicated. Okay, maybe rand. Okay, now I can summarize the model and the wrong model. Uh, in table. Ah, okay. Since I'm using English as a okay, probably I'm adding always a column rand every time. So maybe I have to maybe call it in and check if English. Uh, so array, you see, I've added first a column random, since then a column rand. So I made a mess basically to clean it and come back to the English variable of the dataset because now I've modified it. I don't know how to do it actually. So maybe clear. No, clear pushback. Maybe I have to download it again, download again the package. Uh, no. Yeah, maybe I can clean. So I removed all the objects. Now I can see that they don't have any more, this English variable doesn't have any more the random variable. So let's come back to the model that I have to do again. And let's do this procedure. Okay. Okay, the first model has a multiplier squared of 19. Now I add some predictors, a random predictor, and it will increase this R squared by a little, but it increases because this predictor will help you to explain the variance by chance. But let's look at the adjusted R squared, which has decreased. So this is a sign that the variable we added should have been added, which indeed is the case because I mean I defined a column completely randomly. I cannot use it as a predictor. Okay, does it make sense? If you have questions, it's easy. Okay. I can, I mean, it, is it easy? You already made, you did this. Ah, okay. Okay. But I mean, this, of course, you don't have to learn everything that's here, but you need to know that when you are working with this kind of stuff, where to go and look for them. So it's not really, I mean, it's even useless to learn all of this stuff, but you have to know um, something you have to know, and but if you ever go to the only way of knowing it is by working on it, especially if it is not behind a huge amount of theory. Uh, so this is the adjusted R squared that I wanted to tell you, and that this ends the multiple linear regression, multivariate linear regression. Now, some causality questions, so which are maybe the funnier part. Um, so if you look at some data, um, so for instance, we have variable weight, which has some values, let's say 20, 30, 10, 35, 25. And there is a variable number of words, which is like 1, 5, 0, 6, 2. And we plot them. So now it's, so assume we are taking some children and we are measuring their weight and the number of words they know. So we obtain a picture of this kind, where you see a trend. I mean, you see that the weight influences the number of words. I mean, do you think it is possible, this kind of picture? Do you have some idea of how to explain it? Yes, we are taking children, I guess I mean, probably these are not kilos because I exaggerated, but the weight of a person and the number of words he knows. A children, a guy who is starting speaking, so,
It's, I mean, I think we're missing and then going back to the age. The older the person, I mean, if we compare values, adults way more and they know more words.
Ex-
So, well, this is a correlation.
exactly, it's precisely that. But I mean, this is a picture that you see. I mean, so if you go and probably, so there is not a causal relationship in this sense. There is not that weight influences the number of words. But it's true that you obtain, I don't know, when if you go to a school, you start waiting to a prime, I don't know, if you do this experiment on small-sized children, you will obtain a picture of this kind uh, because yeah, I mean, but of course there is no causal relationship. So this is an example. So more probably, so as we understand, if there is trust, is uh, the causal diagram is the following. So that age influences weight, and age also influences the number of words. I don't know, time spent speaking. If you want really to make a causal relationship, so time spent, I don't know, listening, speaking, etc., etc. And then this influences the number of words. So this is the causal diagram, or at least it's not really. So this is just to say that a causal diagram has much more information than simply the data. It's like an underlying way that you have to add a causal diagram to the data to speak about causality. Um, so probably I have a better picture here. And okay, uh, I don't know if it is better or not, but as a diagram, it's better. So because you can see, okay, so this is called a causal diagram. Age is is a confunding variable. So it explains, uh, it influences uh, like in the same direction uh, uh, age, the weight, and the number of words. Uh, so this is a definition. So simply to be concrete, I don't know. Let's take the way that the weight is. So the age is a uniform. We take children uniformly from the age to I don't know, to 1 to 3 years old. So and we take 20 children. Then the weight, let's say, is 4 times the age plus 4 plus 3 plus a random normal distribution of plus a noise, and the number of words is equal to, I don't know, 4 times the age, 3 times the age, plus a random exponential. And let's plot this data. Uh, okay, I don't know why I'm doing this actually, but okay, here is the data with also the confunding variable together. And you see that if we so the age was the x-axis, so if we remove it, sorry, okay, here we are considering only sorry, the x is this one. So now there is not anymore an x. So we see that the weight, which is the y, has a correlation with the with z, which is the number of words. But if we go up here, there is no causal relationship here. The weight, of course, doesn't have the a number of words inside. There is no number of words inside this expression. And in the number of words, there is no weight to this expression. So this, if we put here also 4 times number of words, this would mean that we are giving some causal effect, for instance, but no. But still, you see correlations. This is the typical example of that independence that does imply that causality imply. I mean that the shark attacks and ice creams are sold are like correlated because the confunding variable in that case is the summer, or if it is summer, there are more shark attacks and more ice cream sold. But okay, so what can we do to check causality relations? The thing that okay, no, let's the thing that one can do something like is like randomized clinical trials, but this is more done by medical research, and I cannot imagine that in linguistics this can be done. So maybe we will speak about it later. And let's go for adjusting for confounders. So this second way of doing it. I mean, let's start by thinking. So, of course, smoking is causally connected to the life expectancy. So, smoking kills. Um, but at the beginning of statistics, at the beginning of statistics, some data was collected. So let's imagine this kind of data. So life expectancy is equal to 90 minus 3 times smoking level. And the smoking level is that let's take an exponential. Yeah, we take so let's plot the data. Something like that. So now mm, at the beginning of statistics, this thing that correlation uh, does not imply causation was well known. So I mean, what can be a justification, an alternative a justification of the above picture that for which this is false, that smoking is causally connected to life expectancy. You look at this data, you see, okay, there is a correlation, but correlation doesn't imply causation. So there can be an alternative explanation. Yes, but the diagram can be shrinked. So if you have something like this, uh, you can it's transitive the relation. So if I influence this influences the other. So this would also lead to a causal diagram like this. You need something else that influences the life expectancy and something which also influences smoking. This is a good explanation. So, but why? Okay, so stress influences smoking, but stress, I don't know, maybe also influences also the alcohol consumption, which and maybe it is this one which causes a low life expectancy. Oh, also yes, yes, but it can be. See, it's not really easy to define what is a causal relationship. It's not, but something about the model. So you have a model like stress, but yes, but how can you check then that which one is more likely to be true? Sorry, I didn't hear. We should like compare people with the same level of stress and which smoke different. I mean, we should collect people with the same amount of stress, but this can be difficult because maybe you need usually in data you have a lot of people and so this is not possible. So, but the beginning is to collect also the data on stress. So this makes sense. So let's actually make a model. So the model is that is the following. We already did it. Uh, so if we go here, we add also stress level. The stress level influences the smoking level, maybe uh, say 1.2 times stress plus exponential, and then here it is mm, random normal, exponential again. So now we have the data. Okay, this is given to you. We have your experiment. And this is hidden to you, this way of generating the data. It would be like a model that you want to discover. What you observe is simply this tuple of X, which has the stress level, the smoking level, and the life expectancy. And we can, well, now the idea is that, okay, if we did a linear regression with the last two variables, what do we obtain? So you obtain a beta 1, which is statistically different from 0. So so we want to predict the life expectancy using the smoking level. And indeed, you find a very small p-value. Well, now we go and we look at the model that you assume that explains both that explains the life expectancy, and we do the same stuff. But we add also the confunding variable, which is the stress level. So in this way, what do we obtain? We obtain this model. So this that the smoking level and the stress level both influence the life expectancy. So we have life expectancy is equal to the intercept, which is 88.9 minus 1.6 times the smoking level minus 2.2 the stress level. So this linear regression what didn't really is an hint in favor of which diagram, this one or the second one? So look at this coefficient. So if we increase, so what we are doing, we are not like trying to find a causal relationship from the data. I give you two kind of different explanations, and you have to accept one of it to say which one is more likely. In this case, there is still an effect in from the life expectancy from the smoking level, even if we added this confounding variable stress level. So this stress level maybe explains the smoking level a little bit, but it doesn't explain the fact that the smoking level is explaining the life expectancy. So it's an hint in favor of that there is still a causal relationship between smoking and life expectancy. I mean, it's not approved by statistics. There are no proofs. Maybe there is another confounding variable that explains, and you didn't come up with this. But you see, it's much more complicated. So, I mean, I find a causal relationship. It's a matter of modeling of the way of which you see the world. Instead, data, you can collect data, whatever. And what you can do is to do something of this kind. So yeah, maybe it is this variable that explain you put it, you collect data on this that variable, and you check if it is true that. So in this case, no, but the typical example, sorry, let me finish with this, of confounding variable of the opposite effect is that like coffee causes heart diseases. Let's say also influences the life expectancy. Let's take again these variables. Smoking level and life expectancy, but let's also add the coffee consumed. So the coffee consumed probably doesn't have effect on the life expectancy, but if you consume coffee, you are more likely to smoke a cigarette after after coffee. I mean, it's the real effect. So it's so probably you can find, let's say that we take some people, we look at the coffee consumed, we look at the smoking level, which is influenced by the coffee consumption consumed. And then there is the life expectancy, which is due only to the smoking level. Again, you don't know how this data are generated. This would be like the world that generates the data. But this is artificial and I'm giving it to you. And now I can still do this linear model and this data on this linear model. And we can check whether which one of these two diagrams is true. That, like I tell you, well, the coffee consumed influences directly the life expectancy. I tell you, no, there is a confounding variable, the cigarette. The coffee consumed uh, influences, sorry, the cigarette influences the coffee consumed, but the cigarette also influences the life expectancy. In this case, I know that since I've generated the data, in this case, I know that this second one is true. So let me see, this should, so, and I decide to take an experiment to see whether it is true, the first one or the second one. Well, of course, sorry, not smoking level, but now it is coffee consumed. On the data, the smoking level, but the coffee. Ah, sorry, no, the smoking level. So in this case, we want to see that the coffee consumed actually has no effect. So we look only at the first model in which I try to predict the life expectancy using the coffee consumed, and they see that there is an effect that the coffee consumed influences negatively the expected life expectancy. Then okay, say okay, no, it is the cigarette actually. So I add to my data the cigarette, the smoking level. And let's see what I see, that the coffee consumed is significantly different, is not significantly different from zero. So you see the p-value is 0.43, and I cannot. So this is an hint in favor uh, of this second diagram, because here it is not significantly different from zero. So you can do this thing to check the causality diagram. So yes, the coefficient of the linear regression, it is different from zero, but you will never find that zero. But it's not significantly different from zero, so you would rather keep the hypothesis. I mean, so this is what you can do. So I don't know. Do you have questions? The, if whatever, just I mean, if it was too slow, if I have to repeat anything uh, too fast, I don't know. You can think about it and tell me the next lecture. Okay, okay. So then see you. It's time. So that's